Hello, class. Let's proceed with the next problem in the topic thermodynamic analysis. Methane. So, by the way, before I start, this example is actually part of the problem set, which I would send to you soon. Methane gas is to be compressed from 100 psi and 80 degrees Fahrenheit to 500 psi. The compressor is to operate adiabatically and is expected to have an efficiency of 80% compared with isentropic compression. After compression, the methane is to be cooled at a constant pressure of 500 psia to a temperature of 100 degrees Fahrenheit. Data for methane is given below. Make a thermodynamic analysis of the process when the T-nat or the temperature of the surroundings 80 degrees Fahrenheit. Um, And also, this is given at 100 psia and 80 degrees Fahrenheit. The enthalpy of methane is 407 BTU per pound. The entropy is 1.45 BTU per pound Rankine. And at 500 psia, this table is given. Okay? Um, so, wait. Not at 500 psia. So, yeah, correct. Okay, at 500 psia, the enthalpy and entropy at different temperatures are given. Okay, let me zoom in so you can see. Okay, so I think no need um to look at the supplementary methane table because everything is given in this problem. All right. So at 100 psia, we can assume that uh anyway, and let's just proceed solving the problem. Okay, let's proceed. The first step is to write the diagram and the given. Let's do that. Okay, we're given a compressor. Let's draw the compressor. And then after the compressor, there's a cooler. Okay, that's the cooler. And then we're given that at P1, so before entering or the inlet of the compressor, the pressure is 100 psia and the temperature T1 is 80 degrees Fahrenheit. We're also given after compression P2 is 500 psia. Okay? And also after cooling the it's cooled at constant pressure, by the way. Therefore, P3 is still 500 psia and the new temperature is T3 equal to 100 degrees Fahrenheit. The efficiency of this compressor is 80%. Okay, and then T-nut, let's put that here. T-nut is 80 degrees Fahrenheit. And also, we assume that compressor is adiabatic. Okay. The other given are written on the problem. I will not rewrite them. The required is thermodynamic analysis. Okay. So since this is a work requiring process, uh, we will use this table. Okay, this is for the work requiring process, wherein the sum of the work ideal plus work loss equal the total work shaft or the actual work. I'm referring to the actual work. Okay, let's go back to the whiteboard. All right. Let's write the, or let's find the properties at each of the point. So this is point 1, point 2, point 3, and this is H in BTU per pound, and then S in BTU per pound runtime. Okay. So at point 1, uh, not sure if this is, but we know that when it enters the compressor, it should at least be a vapor. Not sure if this is superheated vapor. Let me check the table. Unfortunately, the methane tables I have is in SI. Anyway, uh, let's keep writing the state of methane, but we are pretty sure that the compressor can only handle a gas or vapor. So let's write at point 1, H1 is, so P1 and T1, H1 is given, which is 407 BTU per pound. Okay, so this is already given. And then S1 is also given at 1.45 here in the problem. So I think I know the reason why the problem gave the values. It's because um, this is in British units and our tables are in SI units. H2, okay, H2 we don't know. But we know 500 psi. These are the values for enthalpy and entropy, but we don't know T2. Okay, we don't know T2. Okay. We can assume first isentropic expansion. Okay, let's assume isentropic expansion. So at point 2, assume isentropic, isentropic compression. I meant compression. Therefore, S1 equal to S2 prime equal to 1.45. Okay. Um, Therefore, if we assume isentropic compression by interpolation, okay, using 1.45, let's interpolate. So between this value and this value, 1.45 lies here, we can get H2 prime. Okay, H2 prime. So by interpolation, H2 prime is 536.9. Okay. Therefore, we can use the equation for the efficiency to find H2 actual. So efficiency is delta H over delta H. The delta HS is in the numerator, since this is for the compressor, a work requiring device. Therefore, this is H2 prime minus H1 over H2 minus H1, and this is equal to 0.8% or 80%. 80% or 0.8. Next, we solve for H2 um, and this is and substitute. Okay, so rearrange. I'll not show that anymore. Rearrange the equation. So for H2, substitute the values. We get 536.9 minus 407 divided by 0.8, 0.8 plus 407. H2 actual is 569.375. Okay? So we write that on our table, 5 569.375. Now we can get S2 actual. How? By interpolating. Oops. By interpolation of this table using 569.375. So it's between these two. Okay. We will get a S2 actual that's equal to, okay, but I would write that below so that you would remember. By interpolation, S2 actual is 1.49. Okay, let's write that. Alright, so at point 3, this is point 3, we're given already two values, and therefore we can read from the table. So I guess all of these states are gaseous states. Okay. So we write that from the table at P3 500 T100. Okay, this is 408. And this is 1.275. 1.257. I meant 1.257. Now we can proceed with the calculation of the work ideal, work lost, and work shaft. First, let's calculate for the work ideal. I will not write anymore the original equation. So assuming delta P and delta KE are negligible, and if we express work as per pound or per mass basis, then there's no need to reflect the mass of flowing streams. For the work ideal, okay, let me go to the slide. Okay, we're dealing with the entire process. Okay, entire process. So um, that would be from the last point, H3 minus H1. So delta H is H3 minus H1, T naught S3 minus S1. Substituting the values from our table, that's 408 minus 407 minus T naught 80 plus 460, convert to Rankine, do not forget, times S3 minus S1, okay? And you will get 105.22 BTU per pound. That's the work ideal. Now for the work loss, we do this step by step for each of the devices. And the equation is delta S minus Q. First, let's look at the compressor. Alright, so work lost is T naught T naught delta S minus Q. And for the compressor, delta S is S2 minus S1 minus Q. Q12, but since it's adiabatic, this is 0. Okay, so we substitute now the values. One point 49 minus 1.45, and you will get 21.6 BTU per pound. Okay, and next is the cooler. The work loss for the cooler is T naught S3 minus S2, okay, minus Q23. But Q23 is just H3 minus H2. So let's rewrite that, minus H3 minus H2. Okay. Substituting the values, minus H3 minus 569.378. Okay. We will get 35.6 BTU per pound. And finally, for the work shaft, this is the work of the required by the compressor. It's just H2 minus H1. That's 569.375 minus 407, 162.375 BTU per pound. For a work requiring process, it's important to remember, okay, for a work requiring process, the work actual is the sum of the work ideal plus the sum of the work losses. Okay? Therefore, we make the table, and the format of the table is this: work ideal, and then the summation of the work lost. We have two. We have the compressor and the cooler. And the total would give us the work actual. We write now the values of the work, actual values, and also the percentages. So the work ideal that we computed is 105.22. For the compressor, it's 21.6 and 35.6. The sum of the work lost are 57.2. Work shaft is 162.375. In terms of percentages, 64.79, that's the percentage of this of the work ideal. And then this is 13.3, this is 21.91, and this is 100. If we sum this, let me sum that. Oops. Uh, 13.3 plus 21.91, that's 35.21. Okay. And that, now this is our thermodynamic analysis table. So it means that out of the work actual that we inputted, 35.21% of that go went to lost work. Okay, and the work ideal is 64.78% of our work actual. All right, now this ends example number 3. Let's proceed with the next example. Let's proceed with example number 4. A refrigeration cycle is to be used in the production of a continuous supply of chilled water at a temperature of 10 degrees and a rate of 25 kilograms per second. The refrigerant circulating in the cycle is water. Saturated steam at 0.008 bar enters an adiabatic compressor of 80% efficiency based on isentropic operation and is compressed to 0.07 bar. It emerges as saturated liquid from the condenser. The saturated liquid flashes through a valve which acts as a throttle to reduce the pressure to 0.008 bar. The remaining liquid is vaporized in the evaporator, producing saturated vapor. The water to be chilled also passes through the evaporator and by heat exchange with the evaporating refrigerant is cooled down from its feed temperature of 27 to 10 degrees. Make a thermodynamic analysis of the process if T naught is 27 degrees Celsius. Let me pause here to copy and paste the diagram and the process diagram and TS diagram. All right, this is our diagram. So we have the evaporator, compressor, condenser, and throttle valves. This is for a refrigeration cycle using water as refrigerant. Therefore, we can use the steam table for the to determine the properties. And the TS diagram is also shown to help us to find out the state at each point. Let's write the given. Okay. I will write the given on the diagram. Given, we have P1. P1 equal to 0.008 bars. Okay. And we know that such is saturated steam. Okay, saturated steam. Okay. A mix of saturated vapor and liquid. And then next, P2, still 0.008 bars, and it's vapor. Saturated vapor. Okay. Um, Next is P3. Okay, so by the way, there's work here. The efficiency of the compressor is zero point 0.8 or 80%. P3 is 0.07 bar. And then here it's superheated steam, and then we have saturated liquid at zero point 0.4. Saturated liquid. There's an evaporator wherein cooling water at 25 degrees enters. T5 is 27 degrees Celsius and exits at 10 degrees 10 degrees Celsius. Okay, so this is not uh, cooling water. Okay, so this is 37, yeah. Heat exchange and chilled but evaporator. Actually, it's the opposite of cooling is warming water. It's warming water. Heat exchange happens here in the evaporator. Cooling the water. Okay. Cooling the water from 27 to 10 degrees. Okay. So in the previous example 2, the turbine and the condenser, cooling water passes through the condenser. Okay, but in the evaporator, uh, warming water passes through the evaporator. Okay. Next is the required is to make a thermodynamic analysis of the process, and this is quite a long problem. Thermoanalysis. Okay. Let's begin by making a table of the properties at each point. So at point 1, 2, 3, 4, 5, 6, okay, 1, 2, 3, 4, 5, 6, 7, 5, 6 pala, hanggang 6. The state, let's write that. The pressure in bars, and then H in kilojoules per kilogram. And we also write S in kilojoules per kilogram Kelvin. Okay. At point 1, saturated steam. a mixture of liquid and vapor saturated. So instead of bar, let's already transform this to kilopascals. Okay, let's convert to kPa from bars. And the conversion is multiply by 100. So 0.008 bars is zero point 0.8 kPa. And from the steam table, since it's wet, okay, or saturated steam, the problem is we don't know the quality. Okay, we don't know the quality, so let's skip that. Let's go to point 2, saturated vapor. And the same 0.8 kilopascals. Okay. So from the steam table, okay, at P2 equal to zero point 0.8 kilopascal, so you have to interpolate. You have to interpolate. You will get H for the vapor, H vapor 2508. Okay, so this is by interpolation from the steam table, 0.48, and S2 equal to 9.0586. Okay, from the steam table, 0.5861. Let's come. The next is superheated vapor at point 3. Superheated. Right? Tingnan natin. Ayan. So, dito, point 2, saturated vapor, point 3. Okay. At this point, we have to uh, assume, we have to assume isentropic. At point 3, assume isentropic compression. Compression. Okay. And therefore, S2, sorry, S3 prime equal to 9.05861. At 7 kilopascals. Okay, kasi yun yung superheated 7 kilopascal ang value dito, which is actually 0.07 bars equal to 7 kilopascals. From the steam table, read, okay, superheated steam table at 7 kilopascals. Find the H3 prime. So using the S3 prime, H3 prime is interpolate by interpolation. H3 prime is 2791.7. 2791.1. Okay? However, we need H3 And therefore, using for a compressor, diba, delta HS nasa taas over delta H. So this is H3 prime minus H2 over H3 actual minus H2. Solving for H3 actual, substituting the values already. 2791.1 minus 2508.48 divided by the efficiency 0.8 plus 2508.48. H3 actual is 2861.76 kilojoules per kilogram. And therefore, let's write that in on the table. 2861.76. Now we can find S3 actual. Okay. So from the steam table, interpolate S3 actual is equal to 9.295. 9.259. 9.259. Oops. Actually, no. Uh, double interpolation to. Okay, double interpolation. And you will get 9.219. So I hope you know how to do double interpolation. 2219. Dalawang 2. Okay, 2219. So let's write that. Okay. Next is 0.4 saturated liquid. Easy from the steam table. Saturated liquid at 7 kilopascals. Okay. From the steam table, 163, and then this is 0.5591. Okay. And then streams 5 and 6 is the warming water. Okay. I did not write the column for the temperature, so just please write the column for the temperature. So we assume that this water, okay, that passes here, 5 and 6, are saturated liquid. So for to simplify our solution, because we don't have the properties for subcooled liquid. Okay, so it's easier to uh, assume this. And the pressure is, what's the pressure? We don't know the pressure, but we know the temperature. So let's write the temperature instead of the pressure. T5 is 27 degrees Celsius and T6 is 10 degrees Celsius. And we can now use the steam table saturated liquid properties to determine the enthalpy and entropy. Okay. Finally, um, sige, let's circle back to point 1. Since this is a throttle valve, okay, from point 4 to point 1, the throttle valve, therefore, H1 is equal to H4. Okay? Throttling process. Throttling, therefore, H4 is equal to H1 is equal to 163.4. So let's write that in the table. This is 163.4. Okay. And then we can now solve for the quality. We can solve for the quality um, from the steam table. The steam table at P1 equal to 8.8 kPa HV. The HL mo na, HL is 15.825 and HV is 2508.48. Now we can solve for the quality of the uh, steam. So 1 minus x times quality is 0.0592. Right? So now we can solve for S1. Um, we know from the steam table, let's write SL. SL is 0.05 0.05757 and SB is 9.05861. Okay. Solving for S1 using the quality, I just substitute the values. S1 is 0.5904. Okay, so just substitute the SB and SL into this equation and we know X. Now our table is complete. Let's write S. .5904. Our table is complete. We can now proceed with our thermodynamic analysis. Okay, the first step is to calculate for the work ideal. Work ideal, we use the equation. Okay, assume that the work is per kilogram or per mass basis. No need to calculate. Or I mean, no need to input the mass of flowing stream. Assume delta PE and delta KE are 0. Uh, so how do we do this? Okay. Since we're dealing with a cycle, it's quite difficult to find the end and the beginning of our cycle. Uh, but with this, we can actually use these two streams, T5 and T6, to calculate for the work ideal. Okay, we can uh, write H6 minus H5 minus T naught S6 minus S5. Okay, and this would also give us the work ideal. Substituting the values from the table earlier, so I let you substitute, you will get 2.0966 kilojoules per kilogram. Okay? So by the way, I forgot to write that the mass flow rate is also given. Uh, the mass flow rate is given. The mass flow rate is 25 kilograms per second. Okay, but this would refer to the chilled water. Okay, so let me go back to the problem. I told you before that this is the opposite of cooling water. So actually, the correct term is not warming water, but this is in the problem, it's the supply of water to be chilled, okay, from 27 to 10 degrees. Okay, so let's correct the name to chilled water. Okay. The goal of this refrigeration cycle is to chill the water from 27 to 10 degrees. And the mass flow rate of that is 25 kilograms per second. Uh, let's label that as chilled H2O or MC, chilled H2O. Okay. And then let's go back to our. So again, the reason why it's okay to calculate the ideal work using these two streams is because it reflects our goal of chilling the water from 27 to 10 degrees. Okay. This is the result of that, but we have to consider the mass flow rate of the chilled water, and that is 25 kilograms per second. So in fact, we have to multiply that by why? It's because we have two flowing streams, the refrigerant, which is water, and the chilled water, or the water that we're chilling, which is also uh, water. So we have to consider the mass flow rates to correct our energy, or if it, now since it's kilojoules per second, it's now in terms of power. Okay, so we cannot neglect the fact that we have two flowing streams, and therefore we have to correct our calculations, power calculations, to consider the flow rates of the two different streams. So the first stream is the chilled water, which we corrected to by multiplying with the mass flow rate of 25 kilograms per second. I hope that's clear. And this would give us 52.4146 kilojoules per second. Okay? We can now proceed with calculation of actual work. And this is just the work required by the compressor H3 minus H2. Since we don't have any other device, work producing or work requiring device, plug the values from the table, you will get 353.28. But this time we have, okay, very important. We have to multiply with the mass of the refrigerant. Okay? So this time it's the mass of the refrigerant, which is, we don't know yet. We don't know yet. Um, to get the mass of the refrigerant, we can make an energy balance around the evaporator. Energy balance around the evaporator. So this is, we don't know. Evaporator. And actually delta H equal to 0. So we have the delta H of the refrigerant and the delta H of the refrigerant times the mass flow rate of the refrigerant plus the delta H of the chilled water times the mass flow rate of the chilled water equal to 0. And therefore, this is H2 minus H1 times mass of the refrigerant, mass flow rate. And this is H6 minus H5 times the mass flow rate of the chilled water. Okay. We have all the values here. We have H2, H1, H6. We have MC. So now we are able to get, so sulfur MREF, we will get 0.7581 kilograms per second. So we have to multiply this value to this, right? To everything that deals with the refrigerant stream, we have to multiply with the mass of flowing stream of the refrigerant, and everything that deals with the chilled water stream, we have to multiply with the mass of flowing stream of the chilled water. So going back to that, work shaft is 267.82 kilojoules per second. Okay? So I hope this is clear. Just multiply that with that and you get work shaft actual. So now we move on to the work loss. Uh, we have to do this for every device. The equation is, again, this is T naught delta S minus Q. Okay. Versus the compressor. Compressor is uh, work loss equal to, so when we're dealing with the compressor, it's T naught times S3 minus S2, okay, minus Q. But we can assume this is 0 because it's adiabatic given in the problem. Substitute everything and multiply with the mass of the refrigerant, mass flow rate, I mean, you will get 37 point, oops, let me calculate first. 37.15.16 rather kilojoules per second. Okay. And then let's move on to the condenser. Let condenser. The work loss is T naught S4 minus S3 minus Q, but for the condenser, there's heat transfer H4 minus H3. And multiply everything with the mass of the refrigerant. Okay. So everything is already determined. Just plug in the values. You will get 74.46 kilojoules per second. Throttle valve, work loss is T naught S1 minus S4 minus H1 minus H4. But since this is throttling, this is 0. Okay, and then multiply everything by mass flow rate of the refrigerant. Substitute the values 7.12. And finally, the evaporator. So here there are two there's heat exchange. So there are two streams that you have to consider. The first is the um, refrigerant stream. So that's S2 minus S1 times T naught times the mass flow rate of the refrigerant. And okay, very important, you also have to also have to consider the mass flow rate of the chilled water. Okay. I mean, you have to consider the T naught times delta S times mass flow rate of the chilled water. Okay, minus Q. Assuming that there's no heat, there's no heat transfer with the surroundings. This is 0. And then substituting all the values, you'll get the work loss equal to 96.72 kilojoules per second. Now for a work requiring process, okay, work shaft equal to work ideal plus summation of work lost. So we write the table, our work ideal first, and then the summation of the work lost first in the compressor. Next is the condenser, throttle valve, and then evaporator. Okay, and then finally the total would give us the work shaft. And this is in kilojoules per second. Okay? We also need to get the percentage. Now we begin to write the values that we calculated. This is 37.15 and this is 74.46, 7.12, 96.72, and the total is 267.8, and the total work loss is, let me calculate first, 215, 215.45. In terms of percentage, 19.57%, 14.31, 27.36, 2.66, 36.10, and this would give us 100. Okay. When we sum this value, let's see if it is equal. So that's one way, by the way, one way you can check if your computations are correct. When you sum these values, this should equal to the work shaft that oh yeah, it's equal 267.82. Okay, so that means our analysis is correct. I forgot to mention that in the previous examples that your total should match the one that you calculated manually. Okay, using the enthalpies and enthalpy, yeah, the enthalpy. Okay, so that's one way to check. That means that the evaporator has the highest work lost. Okay. This is now the end of our problem. Example 4. I will now stop the video.